Hello everyone, welcome to HighLoad International Conference. My name is Andrei and I will be hosting this event today in this hall. And before we start, a few words about our co-organizer, Yandex, one of the largest IT companies in Europe, specializes in products based on machine learning and neural networks such as search engines, e-commerce and more. Yandex develops open source applications like CatBoost, YDB, YTSaurus, uServer, YAML, and operates in more than 30 countries. Recently, the company opened an office in Serbia, highlighting its commitment to enhance local tech communities. This includes co-organizing HighLoad++, an event aimed at fostering collaboration and innovation within tech industry in Serbia. And without further ado, let me introduce our first speaker, Polina Komissarova, who will tell us how do trucks open their eyes. And luckily, this will help us do the same this lovely morning for those who are still sleepy. So please welcome Polina. The stage is yours.
Hello, everyone. My name is Polina. Sorry. I am a research engineer from the perception team in Never Cargo company, and today I'm going to talk about teaching a self-driving car to see. We will start with a brief exploration of history of autonomous transportation. After that, we will talk about a little bit about different sensors, which can help us to solve this task. And finally, we will gradually move on to the solutions developed and implemented by our team today. But before we start, I would like to tell you a little bit about our company. Cargo is the logistics service provider and one of the first active players in the field of autonomous yard logistics. Our vehicles are entirely developed and assembled by ourselves, and they are autonomous by design, having no driver's cabin and no steering wheel. We employ science and innovations to make logistics more efficient and safe. Our vehicle is not a prototype, it's operating commercially at real client sites, so our experience goes beyond testing polygon and relies on real-life exploitation of our technologies. So let's get back to the topic of our conversation. We would like to create a self-driving car, and first let's talk about clients. Which clients we will create this self-driving for? Our clients are factories, warehouse complexes, or big industrial areas, and closed areas with a wide geography, from Arabic Emirates with a hot desert climate to the polar regions with the extreme sub-zero temperatures and snowfalls lasting for 8-9 months a year. What is interesting about these territories is that there you may find lots of objects which rarely or almost never occur at public streets. For example, different forklifts, robotic mechanisms, various trucks, as well as bricks, pallets, boxes on the roads. So here you can see an example of a real situation in which our self-driving car can find itself at the territory of a warehouse complex. Our car also needs to be fully autonomous, meaning that it has to be able to operate without any human involvement, but it doesn't need to reach high speeds, at least because at these closed territories, the maximum allowed speed for any vehicle is much lower than on the public streets. Okay, we decided to create a self-driving car. How should we start? Let's start from the history. DARPA Challenge is usually considered as the event that gives the major impetus to the development of self-driving cars. It was a competition first organized in 2004 in the United States, and the task was to create an autonomous vehicle capable of traversing a route through the Mojave Desert. The route was about 250 kilometers long, and the participants were given no more than 10 hours to complete it. There was a prize of $2 million at stake, but none of the participants successfully finished the route in 2004. But the next year, in 2005, 5 teams successfully finished the route, and the fastest of them was the team from the Stanford University with the robot called Stanley, which completed the route in less than 7 hours. Let's look at this robot. This robot consisted of different groups of devices. The environment perception system was organized with 5 sensors quite similar to the LiDARs, 1 RGB camera, and 2 radars. GPS system and EMU were used to determine vehicle's position in space. Computations were performed with 6 Pentium M computers located in the trunk, and also various engineering solutions were developed for vehicles control. As we can see, the creation of self-driving car requires the development of lots of systems. But today, let's focus only on the environment perception system. As we can see, it consists of sensors. Robert Stanley used 3 types of sensors: cameras, radars, and LiDARs. Nowadays, almost all companies who are trying to create a self-driving car use combinations of the same sensors, so let's take a closer look at each of them. The first of sensor is camera. Camera is quite simple. It gives us a plain image, which can be color or black and white, and also cameras may vary in the quality of these images and in their field of view. The next sensor is LiDAR. In short, LiDAR is a set of laser beams rotating around the vertical axis and mounted at different angles to the horizontal plane. When laser beam encounters an obstacle, it reflects off it, returns, and by measuring time between sending signal and its return, LiDAR can determine the distance to the obstacle. So, the output of the LiDAR is a 3-dimensional point cloud obtained during the full 360 degrees rotation of the laser beams. In this example, this point cloud was specifically colorized for your better understanding, but even without colors, we can see features of cars, pedestrians, cyclists, trucks, and other objects. The next sensor is radar. Unlike LiDAR, radar operates in the radio wave range, and it also outputs a set of points. But this point cloud is much sparser than the point cloud from the LiDAR. And if we look at this example, it's quite difficult for us to determine to which real objects these points correspond to. It becomes a little bit easier if we correlate these points with the point cloud obtained from the LiDAR, but it's still quite difficult for us to understand these points without information from other sensors. But what is the advantage of the radar is that it can see much further than the LiDAR, so we can detect objects with the radar much earlier than the objects with the LiDAR. Okay, another sensor that was not used in Stanley robot, but which I would like to mention, is sonar. Many of you encountered its operation in regular non-autonomous cars when you use the parking assistance systems. This device helps you to determine whether there are any obstacles on your way in a small radius around the car. Also, all sensors vary in their prices, which also should be taken into account when we are talking about creation of self-driving car, as well as in their perception range. For example, sonar is the cheapest sensor, but it can only see no further than 4 or 5 meters away from the car, whereas radar can see up to 200 meters away from the car, but it costs 10 times more. But also, the performance of different sensors depends on weather conditions and lighting. For example, if we are talking about clear, sunny day, all the sensors perform relatively well. But when the night comes, problems begin with camera, whose perception range decreases a lot, especially at the roads with poor artificial lighting. When we change summer to winter, problems begin with LiDAR, because laser beams also reflect off falling snowflakes, and they appear in our point cloud and can be considered as obstacles on our way, or make the understanding of the surroundings much more difficult. Almost the same situation with fog, because laser beams also reflect off water droplets in the air. And if our clients are located near deserts, we may face quite unusual weather phenomenon, which is called sandstorm. And in this case, we have same problems with cameras and LiDARs. But not only weather should be taken into account. As I already mentioned, at the territories of our clients, we can find lots of small objects on the road, like pallets, boxes, bricks. And they should be detected in order to avoid damaging our vehicle and our cargo. And radars and sonars have problems with detecting these small objects. For example, radar's wavelength doesn't allow it to detect small objects. Okay, after considering all pros and cons of sensors and taking into account the specific needs of our clients, we decided to choose 3 types of sensors. The first sensor is camera, which gives us color image. Second sensor is LiDAR, which gives us dense 3-dimensional point cloud and can operate in any weather conditions after processing the point cloud with specific algorithms, which I'll mention later. And sonar, which is cheap and can help us with blind spots of our LiDAR in a small radius around the car. Okay, we have decided which sensors we will use, but how we can drive automatically with these sensors? Here, of course, we need some algorithms. Usually, the algorithms for self-driving are divided into five steps. Step 1 is called sensing. During this step, we obtain information from all available sensors. For example, this information may contain images, three-dimensional point clouds, GPS coordinates, and so on. The next step is called perception and localization. Having all the information obtained during the previous step, we want to answer two questions. The first question is where we are, meaning that we want to determine our exact position on map. And the second question is what is around us, meaning that we want to determine all the objects like people, cars, as well as traffic signs which will tell us where we are able to continue our movement and with which speed limits. The next step is called prediction. After detecting all moving objects, we want to predict where are they planning to go. For example, where cars are heading, where pedestrians are heading, and so on. And this step is a kind of step 1 for the next step, step planning. When we know plans of all other traffic participants, we can plan our own movements, taking into account where we are going to go. And the final step is called control. At this step, we want to transfer our knowledge about where we are going to move into a specific sequence of mechanical actions, such as steering, accelerating, braking, and so on. Okay, and now again, we see that even the development of algorithms for environment perception requires the development of lots of parts, and usually these tasks are solved separately by different teams in the company. So today, let's only focus on the perception and localization. As we can see from its name, it can be split into two parts. The first part is perception, which is about detecting different objects and determining them. And the second part is about localization, meaning that we want to determine our exact position in space. So these tasks are quite separate. So today, let's only focus on the perception. What is perception? As we have already seen, perception is about processing information obtained from all available sensors. In our case, it's camera, LiDAR, and sonar. To be honest, the information from these sensors can be processed separately. So let's today focus only on the LiDAR perception. Why? First of all, because I'm dealing with the LiDAR perception. And second of all, because our car, LiDARs in our car have a specific place because they have the biggest field of view. Okay, LiDAR perception. What is it? How we can understand what is going on around us with the LiDARs? First, let's look at back at the DARPA challenge and Robert Stanley, and look how LiDAR perception was organized in this car. Let's recall that this competition took place in the desert, so the participants didn't need to analyze difficult traffic situations. And they didn't need to deal with difficult weather conditions. Also, the participants were able to drive in the center of the road and to move as far as possible from the obstacles at the sides of the roads, like piles of the stones, for example. LiDARs that days were much simpler than they are today. Each LiDAR consisted only of one laser beam, and they rotated in the 90 degrees range. And the LiDAR's duty was to detect objects only in 22 meters away from our car, so not so far. The algorithm that the team used was quite simple. They looked at the difference in the height between neighboring points, and if this height was bigger than some threshold value, they considered it as an obstacle. So the idea was quite simple. They didn't use any deep learning algorithms that days, and they didn't need to solve object detection tasks. So what about now? Can we do something better and solve more complicated tasks? Of course, yes, and our algorithm will consist of 3 steps. Step 1 is filtering. This step is particularly important in the conditions such as snowfall, because in this case we have lots of noisy points in our point cloud and we need to filter them out. The second step is called drivable area selection. When we filtered out all the noisy points, we want to determine where we have real obstacles which should be avoided and where we have a drivable area. And the last step is called objects detection. At this step, we want to detect all moving or potentially moving objects. Okay, let's look at each step separately. First step is called filtering. For better understanding why we need this step, let's look at an example of a point cloud obtained during a snowstorm. Snowflakes are specifically highlighted in pink in this example, and we can see a really big amount of these points. And we can't understand if there are any obstacles among them, like real obstacles. And it makes more difficult the understanding of the surroundings. Okay, the algorithm that we decided to choose for filtering these points is called dynamic radius outlier removal. And before we look at this algorithm, let's first look at the data. Let's look at the part of the point cloud obtained during the snow. In the left part of the slide, you can see an example of real obstacles, like pedestrians, corner of the building, a car, and you can see kind of lines in these images. Each line corresponds to one laser beam. And inside these lines, you can see quite high density of points. But if you look at the right part of the slide, you can see an example of point cloud of just snowflakes, and they look like isolated points in the air. So it looks like we can visually distinguish between real obstacles and noisy points, just comparing the density of the points. That's the first thing. The second thing is that the density of points decreases with the distance from the LiDAR. So if we look at the objects in 5 meters away from our car, like a person or a part of the road, we will see quite high density of points. But if we look at the wall or a bag of potatoes in 30 meters away from the LiDAR, we can see much lower density. Let's use these properties to create an algorithm. It is quite simple. Let's look at each point and count the number of neighboring points in some radius. If the number of points is bigger than some threshold, then we consider this point as a real obstacle. So it looks like this point has quite high density. It is a real obstacle. But if the density is lower than some threshold, we consider this point as noise, and we get rid of it. And the distance increases with the distance from the LiDAR because the density decreases with the distance from the LiDAR. And this quite simple algorithm helps us a lot with removing snow from our point cloud. Okay, next step is drivable area selection. At this step, we want to determine regions where we shouldn't move in order to avoid collisions. In this step, we will use neural networks. Why? Because they developed a lot since the DARPA challenge, and nowadays almost all companies who are dealing with creation of self-driving car are using neural networks because in computer vision they developed a lot. Usually, creation a neural network requires the development of 3 steps. The first step is data collection, during which we collect data for training the neural network. The second step is data annotation, when we tell which points correspond to which classes, for example, obstacles or real road points. And the last step is neural networks training, using all this annotated data. Okay, let's look at each step. First of all, we need data. Where can we get data? Simple answer is open source. There are really lots of data available open source, and also data for LiDAR perception, but there is a problem with this data called domain shift. Let's look at these 2 images. First of all, we can see these kind of circle patterns at each of these images. These circle patterns are obtained when the LiDAR laser beam rotates and encounters a road. And when they complete this 360-degree rotation, we see these circle patterns. In the left image, we can see these circle patterns are concentric. But in the second image, we can see that they are intersect. That's the first thing. And the second thing that we see that in the left image, the density of these circle patterns is much higher than in the right image. Why? Because the first image was obtained from one LiDAR, so there are only concentric circles, and the second image was obtained from 2 LiDARs. They are mounted at different positions, so these circle patterns intersect. And also, the first LiDAR consisted of 64 laser beams, but the image from the second image was obtained from 2 LiDARs consisted of 32 laser beams. The more laser beams we have, the bigger the density of the points. The left image was obtained from the open source, and the right image is from our car. So we see that they are quite different. And if we train our neural network on the images like on the left-hand side, it looks like it will perform poorer on our real data. Another thing is that almost all open source datasets were collected at real public streets. So these datasets consist of lots of cyclists, traffic lights, and so on. And our neural network will be good in detecting, for example, cyclists. But in our industrial areas, we see cyclists not so often. But we see lots of trucks, lots of forklifts, robotic mechanisms, which we can't find at real public streets. And that is the domain shift. The problem is that we have different data in our open source data sets and in our real data. Okay, what is the solution? Imagine that you haven't created your self-driving car fully. You haven't created all the systems, but you already want to solve perception tasks. You want to collect data, and the solution is called sensor unit. You can create a kind of device consisted only of your sensors, only of your sensors which you are going to use. It can be quite simple, made of tape, but you can also invite your engineers to create a kind of better device where all the sensors are located exactly at the places where they will be located in your real car. Okay, and this is this thing which will help us to collect the data. This thing can be mounted at any vehicle, no matter if it is self-driving or just simple car. Okay, we have collected data. What should we do? Annotate it. Okay, but here is another problem. The annotation of 3-dimensional point clouds is very time-consuming, very expensive, and difficult. It is much more difficult than annotation of 2-dimensional images. And so we cannot annotate everything. We need to select data specifically for our needs. We need to find some specific data. For example, we need to find data with these small obstacles on the road. But how can we find it among all the data which we have collected? Here, we decided to use one of open source neural networks, which is trained on images. What can this neural network can do? It can detect objects of any classes. For example, boxes, pallets, people, cars, dumpsters, and so on. So we can ask this neural network to detect any small objects. But wait, we don't have images, we have point clouds. Let's remember that in our sensor unit, we have all the sensors which we are going to use. So we can take images corresponding to our point clouds, so collected at the same time as these point clouds. So we will find obstacles in these images, and then we will take the point clouds corresponding to these particular images. And that is how we will find interesting point clouds. But we haven't still dealt with the time-consuming annotation. Here our team decided to create another solution. We decided to fuse several point clouds obtained during time. Then we colorized it with the images obtained at the same time. And we looked at this point cloud from the bird's eye view and tell annotators, okay, this is not a 3-dimensional point cloud. This is a 2-dimensional image. And your task is to select road, just to annotate semantic segmentation for the road. That is how we can increase the speed of our annotation. They will annotate it like a 2-dimensional image, and then we will go back to our 3-dimensional point clouds. Okay, that is how we collected lots of interesting data, we annotated it, and it's time to training a neural network. Before we will talk about the architecture of a neural network, let's again look at the data. We have already seen these circle patterns in the point cloud. We already know that they occur when our laser beam rotates and encounters road points. Okay, let's use this property. The problem with training neural network and with using neural networks in self-driving is that it has to be fast. It has to be small and work fast. Because our LiDAR obtains 10 images per second. So our whole pipeline has to work not slower than 10 Hz. Okay, so the problem is that we cannot process each point separately. We want to somehow combine them and process like some sectors. Okay, the idea which we decided to use is to split this point cloud into cylindrical sections. If we look at this point cloud from the bird's eye view, these cylindrical sections will look like this. But if we rotate a little bit our point cloud, we will remember it is three-dimensional, and these cylindrical sectors will look like real cylindrical sectors. So the idea is that we take all points which correspond to one sector and transform them somehow into like one point or one vector per sector. And this is how we will decrease the amount of information we will use. Okay, the whole pipeline is at the upper part of this slide, but we will discuss each part separately. First of all, we will take all the points we have and put them into some small neural network, which will give the vector representation of each point. In order not to have too much mathematical notation in this presentation, let's replace it with some colorful rectangles. Okay, we have a kind of hidden representation of each point. And now we put points of each sector in another neural network called PointNet. And this neural network, also not too big, will transform several vectors from one sector into one vector per sector. And this is how we will decrease the amount of information we will process. Okay, and after that, we need to solve the semantic segmentation task. What is it? This is the task when we have to assign label for each sector. So we need to determine which sectors correspond to the road and which sectors correspond to the obstacles. This neural network is quite similar to the neural network for the same task for two-dimensional data. We won't discuss it in details, but this is the neural network which help us to determine which class each sector corresponds to. But we remember that in each sector we have several points, and they can be both obstacles and roads. We have mistakes here. Let's recall that we have vectors for each point in the beginning, and let's insert this information into our neural network. We will change the architecture a little bit, and this will give us the information about class of each point. And this is how we solve the drivable area selection task. So now we know where we can move, where we cannot move. And the last part is object detection part. First, let's decide which objects we are going to detect. Of course, we need to detect objects which mostly occur at the territories of our clients. This may include pedestrians, cars, trucks, for example. And after that, let's again look at the point cloud. Let's look at this example and see that it looks like when we look at the point cloud from the bird's eye view, we can visually distinguish where there is a road and where there are cars. Here they are. So it looks like if we look from the bird's eye view, we can understand where the objects which we want to find are located. And we can think that neural network will be able to do the same thing. So now let's not use difficult cylindrical splitting. We will do something easier. Let's split our new point cloud into a kind of columns. If we look from the bird's eye view, they will look like just squares. Each square consists of several points. Each point has 3 coordinates and also the intensity of the signal. And if we rotate our point cloud, we will remember it is 3-dimensional, so it's not squares, it's columns. So again, as it was with the drivable area selection, we will transform separate points into one vector per each column. And now it looks quite similar to the image. So it looks like we transformed 3-dimensional data into 2-dimensional. And now we can use something similar to the detection in the 2-dimensional images. So we will use neural networks for objects detection, like in plane images. And this will give us bounding boxes. What is bounding box? Bounding box is the center of the road, the coordinates of the center of the road, as well as its length, width, and height, and also the angle of the rotation and the class. So what this bounding box corresponds to: pedestrian, car, truck, and something else. And this is how this neural network works. So here you can see in orange the cars detected, and in purple the pedestrians detected. Okay, and this is how our whole whole LiDAR perception pipeline looks like. So let's recall what we have seen. First, that history analysis sometimes can be a good idea because there are about 10-15 years from the DARPA challenge, but still the solutions are quite similar. Then there is no common solution for the sensor's choice. You should choose them specifically for your task. So sometimes you don't need LiDARs, sometimes you need them, sometimes it's easier to use them, sometimes not. The next thing is that you don't need for your all systems to be ready. So sometimes you can create a kind of sensor unit just to collect all the data and to start solving perception tasks earlier. And you can see that some tasks still can be done without deep learning. Sometimes classical algorithms can help us even in computer vision tasks. And before choosing algorithms, you should look at your data and maybe find some interesting properties about it that will help you to choose better algorithm. Okay, thank you very much for your attention. If you have any questions, you're welcome.
Thank you very much, Polina. Yes, I already see the hand over here. I will pass my mic here.
Thank you for the beautiful presentation. I have a couple of questions. Can you please rewind to the slide number 87?
Yeah.
Mm-hmm. What's the dimensionality of the input cylindrical sections, and how many parameters in neural network? What is in architecture, and how did you choose the architecture? Thank you.
Okay, thank you for your question. If we're talking about the number of points in the point clouds, usually it is about 100,000 or even more. It depends on the, for example, weather conditions. If we're talking about the architecture, the first part is multi-layer perceptron. It's just simple neural network, just to obtain the vector representation for each point. And as for PointNet, I'm not sure I remember the exact number of parameters, but these parts of our pipeline are quite small so that they are able to work faster. So the biggest part of our pipeline for this task is the next step, so kind of this UNet architecture. So PointNet is a kind of classical part for analyzing the points in three-dimensional point cloud. It works fast just to obtain the vector representation of our points.
Thank you. Yeah, here, please.
Sorry. Just wait for 3 seconds.
One. What type of CPUs and GPUs do you use in your devices to run neural networks?
Yes, if we're talking about devices which are located in our car, we have 2 computers based on, if I'm not mistaken, Intel i7, and they have Yes, they have 2 GPUs. We have 2 GPUs for our neural networks to work in our self-driving car. These GPUs are 1660, if I'm not mistaken. It's from NVIDIA.
Gentleman over there to the right.
Hello, thank you for your presentation. What about crowd and crowdsourcing in your project? I really believe in power of machine learning and deep machine learning and big data and super deep machine learning, but without crowdsourcing, it's using only open dataset and open models. Can you talk more about it? What kind of projects, how you construct the crowd system for self-driving? Thank you.
Yeah, cool question. Thank you very much. So if we are talking about data collection, as I mentioned, it's quite difficult to just get the information from the open source data sets because we have this domain shift problem. So we need to collect our own data. This is used with our sensor unit, or with our cars, for example. And also, what is good about sensor unit is that it can be used at any territory. So, for example, if your car is only allowed to be used at the closed territories, not allowed to be used at some public streets, you need to have some special permissions for usage at specific territories. But if we are talking about sensor unit, it can be mounted at any vehicle, and you can go anywhere you want. So it's just a thing that you put on a regular car, and everyone is okay with that. That's the first thing. The second thing is about annotation. So crowdsource also can help with annotation all this data. But here is a problem that we also need to have some permissions for giving this data to like lots of people. So sometimes we can be afraid that this data will go to our to go to other companies, they will use our data. We don't want this. That's the first thing. And the second thing is that sometimes LiDAR data also can be considered as the data which includes personal data, because we see kind of people and something like that. So we sometimes law doesn't allow us to use crowd, for example, annotators from other countries, something like that. So we thought a lot about this problem, and we decided to use our own annotators. So we have our own annotators who annotate our data.
Gentleman at the center.
How much, in terms of how much data do you need to train your neural network in terms of time recorded? 1 day, 2 days, 1 week, 1 month, 1 year, 10 years?
Yes, that's a good question. First, it depends on which quality do you want to have. That's the first thing. The second thing, it depends on the task you are going to solve. So, for example, for drivable area selection, which is quite a simple task, you don't need so much more data. But, for example, if you are talking about the time which need to collect all the data, it really depends on the task. If we are talking about snowfalls, for example, we cannot collect data of snowfalls during summer. And also, the problem with the LiDARs is a really big problem is the fog. And fog doesn't also occur so often at lots of territories. So you just need to wait. So it really depends on the task you are solving. But okay, for drivable areas, and it also depends on how many sensor units or how many cars you have. So for example, if you have like thousands of cars, they can drive everywhere you want, they can collect different data, and you can collect your data set faster. Otherwise, it takes you much more time. So it's really difficult to tell you how much time you need. So yeah.
Thank you.
Hi, thank you so much for the presentation. I want to ask, do you usually work with customers who expect their areas to be both human-driven cars and self-drive, or you have areas that are planned to be designated only for self-driving vehicles?
Thank you for your question. Yes. Nowadays, we of course work with territories where we have real pedestrians and simple cars, non-self-driving cars, at least because most of these warehouse complexes, industrial areas, they also have different trucks. And of course, these trucks come from the city. They bring this cargo from the city to these closed industrial areas. So anyway, you will face these trucks. But our car is specifically used for these closed areas. Maybe in future we will have only self-driving. So maybe in future we will deal only with these self-driving cars, and it will be easier. We don't need to detect pedestrians who are running in front of our car, something like that, jumping or something else. So yeah, good future.
Another question here.
Thank you for an amazing presentation.
Thank you.
My question is about the future of your industry and your research. So coming from natural language processing, we saw how in the last year, a lot of the specialized problems were completely eliminated. So no one is doing name entity recognition or part of speech tagging. We just have one general purpose model that does everything. And it feels like autonomous driving is going in the same direction, with all the companies like Tesla building huge clusters and building one model, not just for perception, but for end-to-end pipeline. Is it similar to your vision, and do you plan to try something like this next year or this year?
Thanks for your question. Yes, we also are thinking about this combination of different tasks in one neural network, at least because it can work faster. You don't need separate neural networks for each task. It will process a point cloud in one step. Now we don't try it. I have seen some papers in this year that are talking about also this approach to the self-driving. Yes, this is really a good idea. It can also, I don't know, we will have only a few people who will train one neural network. We will get rid of all this camera stuff and something like that. Yeah, so that's a good idea. Really, we are thinking about it. We didn't try it yet, but it's a good idea. Yeah, thank you.
Thank you. Unfortunately, we don't have enough time. I encourage you to grab our speaker and go to the discussion zone there. We have a few formalities left. Please rate the talk. Don't be shy. We definitely needed to get better. We have a special prize for the person with the best question asked. Polina, please, who was the one who's...
Well, I needed to be prepared for that. I think I like the question about annotators and some crowdsourcing. Yeah, so maybe this one.
Please raise your hand.
Yeah.
Yes, the person behind the pillar. So, Polina, thank you. We have a special gift for you as well. So, yeah, another round of applause, please.